And now in this lecture I'll answer two questions. In the first question we find out the area of this green shape, and in the second question we find out the length of line segment AP is equals to x using two different methods. So we start with the first question. In the drawing we have a semicircle, BC equals to 8 units in its length, BC equals to 10 units in its length, that is to say the diameter of this semicircle equals to 10 units. In addition, we know that PC equals to 8 units. This is angle ABC. This is the right angle. Again, our task is to find out the area of this green shape. So in the first step, we join points B and P together by straight line. We join points B and P, created peripheral angle BPC. Peripheral angle BPC subtend on BC, that is the diameter of this semicircle. And according to Rule 5, any peripheral angle that subtends on the diameter of the semicircle or circle must be equal to 90 degrees in its size. So we click quickly on Rule 5. According to Rule 5, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. In the drawing we have a circle, and AB is the diameter of this circle. Peripheral angle AB subtends on AB, that is the diameter of this circle, and therefore according to this Rule 5, the size of peripheral angle AB is 90 degrees. So we can implement Rule 5 in our drawing. Because in our drawing we have peripheral angle BPC that subtends on BC, the diameter of this semicircle, and therefore according to Rule 5, peripheral angle BPC must be equal to 90 degrees in its size. In the next step, we will implement the Pythagoras theorem on this right triangle BPC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So in the right triangle BPC, BC is the hypotenuse, therefore the square of the hypotenuse is BC square, and it is equals to PB square plus PC square. So according to the Pythagoras theorem, in this right triangle PBC, BC square, that is the square of the hypotenuse, equals to PB square plus PC square. BC is 10, therefore BC square is 10 squared, it is 100, and it is equals to PB square. PB is the missing side, so leave it as it is, so it will be PB square plus PC square. PC is 8, therefore PC square is 8 squared, it is 64. So in total, if you found out that 100 equals to PB square plus 64. Here we subtract 64 from this equation, and we get that PB square equals to 100 minus 64 is 36. PB square equals to 36. Here we take root out of this equation, and finally we get that PB equals to the square root of 36, that is 6. So the missing side PB is equal to 6 units in its length. It is given as the question that AC is a straight line. So if you focus on the left side of the straight line AC at point P, here the sum of the angles must be equal to 180 degrees, according to the rule that said that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AC at point P? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle APB, we define this angle PAB as alpha. So this angle equals to alpha. This angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. The big angle ABC is 90 degrees according to what is given as the question. This is the big angle ABC, that is the right angle. So what is the size of this missing angle PBC? The size of this missing angle PBC. Actually, the size of this missing angle must be equal to the size of the big angle, that is 90 degrees, minus this angle, that is 90 degrees minus alpha. 90 degrees minus alpha is alpha. So, also can explain why this angle equals to alpha. This angle equals to alpha because alpha plus 90 degrees minus alpha is 90 degrees. That is the size of the big angle ABC. Angle ABC equals to 90 degrees in size. So alpha plus 90 degrees minus alpha is 90 degrees. For that reason, this missing angle must be equal to alpha. So in the right triangle BPC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. In the next step, we prove that the right triangle ABP is similar to the right triangle BPC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So I can prove that all the angles of the right triangle APB are correspondingly equal to all the angles of the right triangle BPC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So write it down, and we found out that the right triangle APB is similar, this is the sign of similar, to the right triangle PBC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle ABP over side BC of the right triangle PBC is equal to side AP of the right triangle APB over side PB of the right triangle PBC. And also that side PB of the right triangle APB is equal to side PB of the right triangle APB over side PC of the right triangle PCB. Actually, side PB is a common side that belongs to both triangles. So repeat again, I should found out that from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB of the right triangle APB or side BC of the right triangle PBC is equal to side AP of the right triangle APB over side PB of the right triangle PBC. It is also equal to side PB of the right triangle APB over side PC of the right triangle PBC. AB is the missing side, so we limit the CT. over BC. BC is 10, and it is equals to AP. AP is the missing side, so we leave this it is. Over PB. PB is 6, and it is equals to PB, it is 6, over PC. PC is 8. So in total, we found out that AB over 10 equals to AP over 6 equals to 6/8. So actually, those two expressions are equal to each other. Therefore, we get the first expression from those two expressions. So according to the first equation, AP over 6 equals to 6/8. AP over 6 equals to 6/8. Here we will multiply this equation 1 by 6, and we get that AP equals to 6 times 6 is 36 over 8. So here we will divide both the numerator and the denominator of this number by 4, and we get that 36 over 4 is 9, and 8 over 4 is 2. So in total, we actually found out that AP equals to 9/2. Okay, again, we should find out that the length of this side AP is 9/2. Those two expressions are also equal to each other. Therefore, we get the second equation from those two expressions. According to the second equation, we get that AB over 10 equals to 6/8. Again, AB over 10 equals to 6/8. Here we will multiply this equation 2 by 10, and we get that AB equals to 10 times 6 is 60 over 8. AB equals to 68. So here we will divide both the numerator and the denominator of this number by 4, and we get that 60 over 4 is 15, 8 over 4 is 2. So in total we should find out that AB equals to 15/2. Actually, this is side AB, this equals to 15/2 units in its length. In the next step, we define the center of this semicircle. This point is point O. The diameter of this semicircle is BC, that is 10, therefore the radius must be equal to 5. The radius OB is 5. The radius OC is also 5. We join points O and P together. We join points O and P together by straight line. OP is of course the radius of the semicircle, that is equals to 5. In the next step, we will define angle POB. This angle is theta, and I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle POB. Actually, the law of cosines is true in any triangle. This is triangle ABC, that could be any triangle. The length of side AB is 8, side AC equals to B units in itself, side BC equals to C units in itself. This is angle BAC, the size of angle BAC is theta degrees. So in this triangle ABC that could be any triangle, the following equation is true. That cosine theta equals to a squared plus b squared minus c squared over 2 times a times b. Again, cosine theta equals to a squared plus b squared minus c squared over 2 times a times b. We can actually implement the new rule, the law of cosines, in this triangle, triangle POB. So in triangle POB, according to the law of cosines, the following equation is true, that cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. It again, according to the law of cosines, in this triangle POB, the following equation is true, that cosine theta equals to 5 squared plus 5 squared minus 6 squared over 2 times 5 times 5. So cosine theta equals to 5 squared is 25 plus 5 squared is 25, so 25 plus 25 is 50, minus 6 squared it is 36, over 2 times 5 times 5, 2 times 5 times 5 is 50. 50 minus 36 is 14 over 50. So in total we should remember that cosine theta equals to 14 over 50. We would like to find out the value of theta itself. So how can we find out the value of theta itself? We use the rule that the inverse function of a function cancels out the action of the function. And again, the inverse function of a function cancels out the action of a function. Actually, I will give you an example. We have the function square and the inverse function of a square is a root. Again, the inverse function of a square is a root. So if we take number 3, for example, and we square it, the result is 9. Now, in order to get back 3 again, you just have to operate on the result that is 9, the inverse function that is root or square root, and you get that the square root of 9 is 3. Actually, you can derive from it that the square, that is the inverse, the root that is the inverse function of a square, cancels the action of a square, because we actually operated the function square on the number 3 and the result is 9. Then we operated the square root on 9 and the result is 3. That is to say, the root cancels the action of a square and we get back 3 again. So repeat again that the inverse function of a function cancels out the action of a function. Here, the inverse function of a square is a root, and the root cancels out the action of a square, because the action of a square is the square of 3, that is 9. Now we operated the inverse function of a square that is a root, and we got back 3 again, because the root of the square root of 9 is 3. So we operated the function cosine on theta, on angle theta. In this way, the result of operating the function cosine on theta is 14 over 50. Now, in order to get back theta again, we just have to operate the inverse function of a cosine, that is our cosine, on the result that is 14 over 50. In this way we get angle theta again. Okay? And arc cosine of 14 over 50 is equal to theta, and theta equals to 73.74 degrees in its size. Actually, you can find out the value of theta by using any simple scientific calculator, and you get that arc cosine of 14 over 50 is 73.74 degrees in its size. So if you found out that this is angle theta, the size of angle theta is 73.74 degrees. Our task is to find out the area of this green shape. In order to find out the area of this green shape, first of all, we have to find out the area of segment BP. This is segment BP. So what is the area of segment BP? From the drawing, it is very easy to see that the area of segment BP is equal to the area of sector BOP. This is sector BOP. Minus the area of this triangle, triangle BOP. So repeat again, we should find out that the area of segment BP is equals to the area of sector BOP minus the area of this triangle, triangle BOP. So what is a sector? A sector is a portion of a circle with two radii and the arc between them. And again, the green shape AOB is a sector. Sector AOB consists of two radii and the arc AB between them. Angle theta is the angle between the two radii. It is also defined as the angle between the legs of the sector. The two radii are defined as the legs of the sector. So what is the area of the sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is to say pi r squared, because the radius is r, times the angle between the legs of the sector, that is theta, over 360 degrees. Again, the area of this sector AOB, the green sector AOB, equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. So we will use the new formula in order to find out the area of this sector, sector BOP. The angle between the legs of the sector, we found out that theta equals to 73.74 degrees in its size. BO equals to 5, this is the radius of the semicircle, and PO also equals to 5. So the area of this sector BOP equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees, over 360 degrees. R is 5, therefore r squared is 5 squared, that is 25, so pi r squared is 25 pi times 73.74 degrees over 360 degrees. In total, the value of this expression is equal to 16.088 square units. So we found out in total that the area of this sector POB is equal to 16.088 square units in its size, minus the area of this triangle POB. BO is 5, PO is also 5. We only found out that PB equals to 6. So triangle POB is defined as an associated triangle because side OB equals to side OP equals to 5. The base of this associated triangle is PP. In order to find out the area of this associated triangle POB, we'll have to, from the vertex O, we'll draw perpendicular on PB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and the base PB. This point is point M. According to the rule that actually we have the rule that says that the perpendicular to the base of an associated triangle bisect the base. The base is PB. So the perpendicular from point O on the vertex PB bisect vertex PB. PB is 6, therefore each half must be equal to 3. The first half PM is 3 and the second half MB is also 3. Now we have to find out the value of OM. In order to find out the value of OM, we just have to implement the Pythagoras theorem on the right triangle POM. According to the Pythagoras theorem, in the right triangle POM, 5 squared, that is the square of the hypotenuse, equals to OM square plus PM square. 5 square is 25, and it is equals to OM square plus PM square. PM is 3, therefore PM square is 3 squared, that is 9. So 25 equals to OM square plus 9. Here we subtract 9 from this equation, and finally we get that OM square equals to 25 minus 9 is 16. So here we take a root out of this equation, and finally found out that OM equals to the square root of 16, that is 4. So the missing height OM is 4. Now it is very easy to find out the area of this associated triangle POB. The area of this associated triangle POB must be equal to the base PB times the height to the base, that is MO, over 2. PB is 6, MO is 4 over 2. 4 over 2 is 2, and 2 times 6 is 12. So in total we should find out that the area of this associated triangle POB is equal to 12 square units in its size. So actually, the area of segment BP is equal to the area of this sector POB, that is 16.088, minus the area of this associated triangle POB, that is 12. And 16.088 minus 12 is equal to 4.088. So if you found out that the area of segment BP is equal to 4.088 square units in its size. But again, the area of segment BP is equal to 4.088 square units in its size. Our task is to find out the area of this green shape. So what is the area of the green shape? the area of the green shape equals to the area of the right triangle APB minus the area of this segment BP, which is equals to the area of the right triangle ABP minus the area of this segment, segment BP. Repeat again, the area of the green shape, that is the area that we are looking for this question, it is equals to the area of the right triangle APB minus the area of segment BP. Side AB equals to 4.5, 9 over 2 is 4.5. Side BP equals to 6 units in its length. So the area of the right triangle ABB is equals to the base AP times the height to the base, that is PB, over 2. AP is 4.5, PB is 6, divided by 2. 4.5 times 6 is 27, divided by 2. 27 over 2 is 13.5. So in total, we should find out that the area of this right triangle APB is equals to 13.5 square units in its size, minus the area of segment BP. We already found out that the area of segment BP is equal to 4.088 square units. So 13.5, that is the area of the right triangle APB, minus 4.088 is equals to 9.412 square units. So in total, we should find out that the area of the green shape, that is the area that we're looking for this question, is equal to 9.412 square units in its size. Repeat again, we should find out that the area of this green shape is equals to 9.412 square units in its size. So we finish with the first question. In the next step, I will present you the second question, and we'll solve the second question by using two different methods. In the second question, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the drawing, we have a semicircle. AB equals to 10 units. That is to say, the diameter of this semicircle is equal to 10, therefore the radius must be equal to 5. In addition, we know that line segment BC equals to 6 units in length. AP equals to PC equals to x. Again, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the first step, we'll define the center of this semicircle. This point is point O. Again, the diameter AB is 10, therefore the radius OA is 5. The radius OB is also 5. In the next step, we'll join points O and P together by a straight line. OP is also the radius of this semicircle, therefore it is equal to 5 units in its length. By doing all those constructions, we created the associated triangle, triangle AOP. Why triangle AOP is an associated triangle? Because side AO equals to side OP equals to 5. And we have the rule that says that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides in the associated triangle, triangle AOP, we have those two angles that must be also equal to each other and their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the associated triangle, triangle AOP, alpha plus alpha is to alpha. Therefore, this third missing angle must be equal to 180 degrees minus 2 alpha. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, triangle, the big triangle, triangle APC is also an associated triangle. Why? Because AP equals to PC equals to X. So, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the big associated triangle, triangle APC, alpha plus alpha is 2 alpha, therefore this third missing angle must be equal to 180 degrees minus 2 alpha, according to the third rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I'll copy the big associated triangle, triangle APC, and the small associated triangle, triangle AOP in a new page, and we'll prove that those two associated triangles are similar to each other according to angle similarity rule. But before that, what is the length of side AC of the big associated triangle, triangle APC? AC equals to in total to 10 plus 6, that is 16. So side AC equals to 16 units in its length. Okay, those are the two associated triangles that are coming from the original drawing. This is the big associated triangle, triangle APC, and this is the small associated triangle, triangle AOP. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are also equal, they are both equal to alpha, therefore they are equal to each other. So if you prove that all the figures of the big associated triangle APC are correspondingly equal to all the figures of the small associated triangle AUP, and therefore those two associated triangles are similar to each other according to angle similarity rule. So I write it down. We should find out that the big associated triangle APC, this associated triangle, is similar. This is the sign of similar to this small associated triangle AOP, according to angle similarity rule. And from the fact that those two associated triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AC of the big associated triangle APC over side AP of the small associated triangle AOP is equal to side PC of the big associated triangle APC or side PO of the small associated triangle AOP. AC is 16 over AP. AP is X, and it is equal to PC. PC is also X over PO. PO equals to 5 units in its length. So in total we should find out that 16 over X equals to X over 5. Here we cross multiply this equation and finally get that X times X is X squared equals to 16 times 5. So here we take a root out of this equation and finally get that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only 5. 4 times square root of 5 is 8.94. So in total we should find out that AP is equals to X it is equal to either 4 times square root of 5 units, or in terms of numbers, AP is equals to X is equal to 8.94 units in its length. Okay, again we should find out that the length of this line segment AP is equals to X. It is equals to either 4 times square root of 5 units in its length, or in terms of numbers, AP is equals to X is equal to 8.94 units in its length. So we finish with the first method. In the next step, I present to you how to find out the length of line segment AP is equal to X according to the second method. In the second method, we use the rule that we have already found, used in the first question. According to the rule, the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. The big triangle APC is an associated triangle because side AP equals to side PC equals to X. The base of the associated triangle APC is AC. AC in total equals to 10 plus 6, that is 16. So the length of the base AC of the associated triangle APC is equal to 16 units. So from the vertex V, we draw perpendicular on the base AC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. We define the touching point of the perpendicular from point P and AC. This point is point M. According to the rule that I mentioned, the perpendicular PM to the base AC bisect the base AC. AC in total is 16. Therefore, the half of AC is 8. So the first half AM is 8, and the second half MC is also 8. According to the rule that I mentioned, and we used it in the first question. AM equals to 8 units in its length. MC also equals to 8 units in its length. In the next step, we define the center of this semicircle. This point is point O. The diameter of this semicircle AB is 10, therefore the radius is 5. The radius AO is 5, and the radius OB is also 5. We join points P and O together by a straight line. PO is of course the radius of this semicircle, that is equals to 5. What is the length of the small line segment OM? From the drawing it is very easy to see that OM in total equals to AM minus AO. Again, OM equals to AM minus AO. So write it down. OM equals to AM minus AO. So OM equals to AM. AM is 8 minus AO. AO is 5. That's the radius of the semicircle. OM equals to 8 minus 5, that is 3. So OM equals to 4 units in its length. So in the next step, I'll copy the right small triangle POM in a new page and we implement on it the Pythagoras theorem. Here by PT is a abbreviation for Pythagoras theorem. So actually, this is the right small triangle OPM that I copied from the original drawing. This right triangle APM, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. So write it down. PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, that is 25, and it is equals to PM squared. PM is the missing side, so we leave it as it is. So it is PM squared plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total we should find out that 25 equals to PM squared plus 9. Here we subtract 9 from this equation and finally get that PM squared equals to 25 minus 9 is 16. So PM squared equals to 16. Here we take a root out of this equation and finally get that PM equals to the square root of 16, that is 4. So the missing side PM equals to 4 units in its length. So this is the missing side PM, that is equal to 4 units in its length. In the next step, I'll copy the right big triangle APM in a new page and we will implement on it the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. Side AM of the right triangle APM equals to 8 units in its length. The hypotenuse AP equals to X, that is the line segment that we are looking for in this question. And PM, side PM equals to 4 units in its length. So actually, this is the right triangle APM, this is according to the original drawing. This right triangle APM according to the Pythagoras theorem, PA squared, that is the square of the hypotenuse, equals to PM squared plus MA squared. So I write it down. PA squared, that is the square of the hypotenuse, is equal to PM squared plus AM squared. The hypotenuse PA equals to X, therefore PA squared is X squared, and it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, it is 16. Plus AM squared. AM is 8, therefore AM squared is 8 squared, it is 64. So in total we should find out that X squared equals to 16 plus 64, that is 80. So X squared equals to 80. Here we will substitute 80 by 16 times 5. So X squared equals to 16 times 5. So here we take a root out of this equation. And finally we get that X equals to the square root of 16 times 5. The square root of 16 is 4. Inside the root we left only 5. So in total we actually found out that AP that is equal to X. Actually in both methods we found out that AP that is equal to X is equal to either 4 times square root of 5 units in itself, in terms of numbers. AP that is equal to X is equal to 8.94 units in its length. If it again, I actually found out that in both methods we found out that the length of line segment AP that is equal to X, it is equal to either 4 times square root of 5 units in its length, or AP that is equal to X, it is equal to 8.94 units in its length. So we finish with the second question. In the next step I present to you, I will summarize the lecture. We start with the first question, of course. Our task in the first question is to find out the area of this V shape. So in the drawing we have a semicircle. BC equals to 10 units in its length. This is to say the diameter of this semicircle is equal to 10 units. In addition, we know that PC equals to 8 units in its length. This is angle ABC, this is a right angle. Again, our task is to find out the area of this V shape. So first of all, we join points P and B together by side line. By joining points P and B, we created peripheral angle BPC. Peripheral angle BPC subset on BC, that is the diameter of this semicircle, and according to rule 5, any peripheral angle that is subset on the diameter of the semicircle must be equal to 90 degrees in its size. Therefore, peripheral angle BPC, this angle, is a right angle according to rule 5. In the next step, we implemented the Pythagoras theorem on the right angle BPC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right angle BPC is BC, therefore the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. Repeat again, according to the Pythagoras theorem of the right angle BPC, BC square equals to PB square plus PC square. So BC is 10, therefore BC square is 10 square, and it is equals to PB square. PB is the missing side, so we leave it as it is. So it is PB square plus PC square. PC is 8, therefore PC square is 8 square, that is 64. So in total we should find out that 100 equals to PB square plus 64. Here we subtract 64 from this equation, and finally found out that PB square equals to 100 minus 64 is 36. Here we took a root out of this equation and found out that PB equals to the square root of 36, 36. So the missing side PB equals to 6 units in its length. It is given us the question that AC is a straight line. So if we focus on the left side of the straight line, AC at point P, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of AC at point P? We have this angle that is right angle plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right angle APB, we define angle BAP, this angle is alpha, so this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in a triangle. We know that the big angle ABC is a right angle. So the size of this missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees. This is the size of the big angle ABC. You can see it in another way. Why the size of this missing angle must be equal to alpha? Because the size of the big angle ABC is 90 degrees. So 90 degrees minus the size of this angle, that is 90 degrees minus alpha, must be equal to alpha. And indeed, 90 degrees minus 90 degrees minus alpha is equals to alpha. So the size of this missing angle equals to alpha. So this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because if we relate to the right angle BPC, alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. In the next step, we prove that the right angle ABP is similar to the right angle PBC according to angle similarity rule. So why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you find out that all the figures of the right angle APB correspond equal to all the figures of the right angle PBC, and therefore those two right angles are similar to each other according to angle similarity rule. So if you find out that the right angle ABP is similar to the right angle PBC according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides. We derive the side AB of the right angle APB over side BC of the right angle PBC is equals to side AP of the right angle APB over side PB of the right angle PBC, and it is also equals to side PB of the right angle APB over side PC of the right angle PBC. And again, on the fact that those two right angles are similar to each other, we derive that AB over BC equals to AP over PB equals to PB over PC. In the numerator of this expression, of each expression, we have the sides of the right angle APB, and in the denominator of this of each expression, we have the sides of the right angle PBC. So AB over BC equals to AP over PB equals to PB over PC. And PB is the common side that belongs to both triangles. AB is the missing side, so we limit cities over BC. BC is 10 over AP. AP is the missing side, so we limit cities over PB. PB is 6, and it is equals to PB again, that is 6 over PC. PC is 8. So in total, we should find out that AB over 10 equals to AP over 6 equals to 6 eighths. Those two sides are equal to each other, therefore we get the equation 1 from those two sides, from those two expressions. According to equation 1, AP over 6 equals to 6 eighths. AP over 6 equals to 6 eighths. Here we multiply this equation by 6 and finally found out that AP equals to 6 times 6 is 36 eighths. AP equals to 36 eighths. Here we divided both the numerator and the denominator of this number by 4. 36 over 4 is 9 and 8 over 4 is 2. So total we should find out that AP equals to 9 halves. This is the missing sign AP, this is equals to 9 halves. Likewise, those two expressions are also equal to each other. Therefore we can get equation 2 from those two expressions. According to equation 2, AB over 10 equals to 6 eighths. And again, we actually found out that AB over 10 equals to 6 eighths. Here we multiply this equation 2 by 10, and finally found out that AB equals to 10 times 6, that is 60 eighths. Here we divided both the numerator and the denominator of this number by 4, and found out actually that 60 over 4 is 15, and 8 over 4 is 2. So in total we actually found out that the length of the missing side AB is 15 halves. And again, we found out that the length of this missing side AB is equal to 15 halves. So, in the next step, we defined the center of this semicircle. This point is point O. The diameter BC is 10, therefore the radius BO is 5, the radius OC is also 5. We join points on P together by a straight line. OP is also the radius of this semicircle, that is equals to 5 units in its length. By doing all those this construction, we created triangle POB. We defined this angle POB is theta. Then I presented to the law of cosines and implemented the law of cosines in this triangle POB. This is triangle ABC. So the law of cosines, what is the law of cosines? The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. This triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. This is angle BAC that is equal to theta degrees in its size. In this triangle ABC that could be any triangle, the following equation is 2. That cosine theta equals to A square plus B square minus C square over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square over 2 times A times B. So in the next step, we implemented the law of cosines in this triangle POB. According to the law of cosines, in this triangle POB, cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. And again, this triangle POB, according to the law of cosines, cosine theta equals to 5 square plus 5 square minus 6 square over 2 times 5 times 5. So cosine theta equals to 5 square. 5 square is 25, plus 5 square, that is 25. 25 plus 25 is 50. Minus 6 square. 6 square is 36. So in total, the numerator we have 50 minus 36, that is 14. In the denominator we have 2 times 5, that is 50. So in total, cosine theta equals to 14 over 50. Again, cosine theta equals to 14 over 50. We would like to find out the value of theta itself. So how can find out the value of theta itself? We'll use the rule that said that the inverse function of a function cancels out the action of a function. Again, the inverse function of a function cancels out the action of a function. For example, the inverse function of a square is the root. Again, the inverse function of a square is the root. If we take number 3 and we square it, the result is 9, because 3 squared is 9. Now, in order to get back 3 again, we have to cancel the operation of a square. Therefore, we use the inverse function of a square, that is a root, and we operate it on the result, that is 9. And indeed, the root of 9 is 3. So actually, the inverse function of a square, that is the root, cancels the action of a square. Because we get, by using the inverse function on the result, we get back the value of 3 again. Okay? From this example, we can conclude that the inverse function of a function cancels out the action of a function. So, in order to get back angle theta again, we have to operate the inverse function of cosine, that is r cosine, on the result, that is 14 over 50. So r cosine of 14 over 50 is the value of theta itself. And r cosine of 15 over 50 is 73.74 degrees. So in total, we should find out that angle theta equals to 73.74 degrees in its size. This is angle theta, that is equals to 73.74 degrees in its size. Our task is to find out the area of this green shape. In order to find out the area of this green shape, we have to find out, first of all, the area of this segment BP. So what is the area of segment BP? The area of segment BP equals to the area of sector BOP minus the area of this triangle BPO. Again, the area of this segment BP equals to the area of segment BPO, the area of sector BPO minus the area of this triangle BPO. And again, the area of segment BP equals to the area of sector BPO minus the area of triangle BPO. What is a sector? A sector is a portion of a circle with 2 radii and the arc between them. It again. The green shape AOB is a sector. Sector AOB consists of 2 radii and the arc between the 2 radii, arc AB. Angle theta is the angle between the legs of the sector, and the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. We use the new formula in order to find out the area of this sector, sector POB. The area of this sector POB must be equal to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 73.74 degrees, over 360 degrees. R is the radius of the semicircle, that is 5. Therefore, r squared is 5 squared, that is 25. Pi r squared is 25 pi times 73.74 degrees, that is the angle between the legs of the sector, over 360 degrees. The value of this expression in total, it is 16.088. So in total, we should find out that the area of sector BOP equals to 16.088 square units in its size, minus the area of this associated triangle times BPO. Why triangle BPO is an associated triangle? Because BO equals to OP equals to 5. PB is defined as the base of this associated triangle times POB. So in order to find out the area of this associated triangle times POB, we use the rule that we have already used in the first question. Okay, this is the first question. So we use the rule that states that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So from point O, we go perpendicular on the base PB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PB, the base PB, this point is point M. According to the rule that I mentioned, the perpendicular OM bisects the base PB. PB is 6, therefore each half must be equal to 3. The first half PM is 3 and the second half MB is 3. In order to find out the area of this triangle, we have to find out the area of the length of side OM. We use the Pythagoras theorem in order to find out the length of side OM. According to the Pythagoras theorem, in the right triangle POM, PO square equals to OM square plus MO square. PO is 5, therefore PO square is 5 square, equals to OM square plus PM square. PM is 3, therefore PM square is 3 square, that is 9. So total we should find out that 25 equals to OM square plus 9. Here we subtract 9 from this equation, and we found out that OM square equals to 25 minus 9 is 16. So OM square equals to 16. Here we took a root out of this equation, and we found out that OM equals to the square root of 16, that is 4. So the height OM is 4. Now it is very easy to find out the area of this associated triangle, triangle OPM. According to the area of any triangle equals to the base of the triangle times the height of the base over 2. The area of this associated triangle, triangle POM must be equal to the base PB times the height OM over 2. PB is 6, OM is 4 divided by 2. 4 over 2 is 2 and 2 times 6 is 12. So in total we should find out that the area of this associated triangle POB is equals to 12 square units in its size. And the area of 7BP equals to the area of sector POB, that is 16.088, minus the area of this associated triangle POB, that is 12 square units. And 16.088 minus 12 is 4.088. So in total we should find out that the area of 7BP is equals to 4.088 square units in its size. Our task is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the right triangle APB minus the area of this segment VP. Again, the area of the green shape equals to the area of the right triangle APB minus the area of this segment BP. And again, we should find out that the area of the green shape equals to the area of the right triangle APB minus the area of segment BP. What is the area of the right triangle APB? Is equals to the base AP times the height of the base PB over 2. AP is 4.5, PB is 6 divided by 2. 4.5 times 6 is 27. 27 over 2 is 13.5. So in total we should find out that the area of this right triangle APB is 13.5 square units. Minus the area of this segment BP. We already found out that the area of this segment BP equals to 4.088 square units in its size. And 13.5 minus 4.088 is 9.412 square units. So actually found out that the area of this green shape is equal to 9.412 square units in its size. Okay, we finished with the first question. In the next step, I presented you the second question, and you solve the second question by using two different methods. In the second question, our task is to find out the length of line 70 AP, that is equal to x. We have to find out the value of x. So in the drawing we have a semicircle. AB equals to 10, that is to say the diameter of the semicircle is equal to 10 units in its length. Line 7 BC equals to 6 units. AP equals to PC equals to x. Again, our test is to find out the length of line 7 AP, that is equals to x. We have to find out the value of x. So first of all, we define the center of this semicircle. This point is point O. The diameter AB is 10, therefore the radius is 5. The radius AO is 5, the radius OB is 5. We join points O and P together by straight line. OP is also the radius of this semicircle, that is equal to 5. By doing this construction, we created the associated triangle, triangle AOP. Why triangle AOP is an associated triangle? Because AO equals to OP equals to 5. So if we focus on the associated triangle, triangle AOP, we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in the right triangle AOP, alpha plus alpha is 2 alpha, therefore this third missing angle must be equal to 180 degrees minus 2 alpha. According to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the big associated triangle, triangle APC, the big triangle APC is an associated triangle because AP equals to PC equals to X. So in this big associated triangle, triangle APC, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. But we only found out that the size of this angle is alpha. Therefore, the size of this angle must be also equal to alpha because they are equal to each other. In the next step, I copied the big associated triangle APC, and the small associated triangle AOP in a new page, and we proved that those two associated triangles are similar to each other according to angle similarity rule. So actually, those are the two associated triangles that are copied from the original drawing. This is the big associated triangle APC, this is the small associated triangle AOP. So why those two associated triangles are similar to each other? First of all, those two angles are both equal to 180 degrees minus 2 alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So we found out that all the triangles of the big associated triangle APC are correspondingly equal to all the triangles of the small associated triangle AOP. And therefore, those two associated triangles are similar to each other according to angle similarity rule. Okay, similar to each other according to angle similarity rule. And from the fact that those two associated triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive the side AC of the big associated triangle APC over side AP of the small associated triangle AOP is equal to side PC of the big associated triangle APC over side PO of the small associated triangle AOP. AC is 16, AP is X, PC is X, and PO is 5. So in total we found out that 16 over X equals to X over 5. Here we cross multiply this equation and finally found out that X times X is X squared equals to 16 times 5. Here we took a root out of this equation and finally found out that X equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. 4 times square root of 5 is 8.94 units. So in total we found out that AP is equals to X, it is equal to either 4 times square root of 5 units in itself, or in terms of numbers, AP is equals to X, it is equals to 8.94 units in itself. I repeat again, the length of this side 7 AP is equals to X, it is equals to either 4 square root of 5 units in itself, or in terms of numbers, AP is equals to X, it is equals to 8.94 units in itself. So we finished with the first method. In the next step I presented to you how to find out the length of side AP that is equal to X using a second method. In the second method, we used the rule that we have already used in the first question. The rule says that in front of the perpendicular to the base of an associated triangle, bisect the base. Again, the perpendicular to the base of an associated triangle, bisect the base. The big triangle APC is an associated triangle because AP equals to PC equals to X. From the vertex P, we draw perpendicular on the base AC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and AC as M. AC in total equals to 16 plus 10, that is 10 plus 16, 10 plus 6, that is 16. So the base AC in total equals to 16 units in its length. According to the rule that I mentioned, the perpendicular PM bisect the base AC. AC in total is 16, so each half must be equal to 8. The first half AM is 8 and the second half MC is also 8. So in the AP is equals to 5 units in itself. It is the radius of the semicircle. OA is also the radius of the semicircle, that is equals to 5 units. We already found out that AM equals to 8. So what is the length of OM? OM equals to AM minus AO. Again, OM equals to AM minus AO. So OM equals to AM, that is 8, minus AO, that is 5. So in total, OM equals to 8 minus 5, that is 3. So the short answer to OM is equals to 3 units in its length. In the next step, I copied the right triangle OPM in a new page and implemented the Pythagoras theorem on this right triangle OPM. This is the right triangle OPM that I copied from the original drawing according to the Pythagoras theorem. PO squared, that is the square of the hypotenuse, equals to PM squared plus OM squared. PO is 5, therefore PO squared is 5 squared, that is 25, and it is equals to PM squared. PM is the missing side, so we leave it as it is, plus OM squared. OM is 3, therefore OM squared is 3 squared, that is 9. So in total, we should find out that 25 equals to PM squared plus 9. Here we subtract the 9 from this equation, and find out that PM squared equals to 25 minus 9, that is 16. Here we took out of this equation, and find out that PM equals to the square root of 16, that is 4. So the missing side PM equals to 4 units in its length. In the next step, I go with the right big triangle PMC, PMA in a new page, and we implemented the Pythagoras theorem on this big right triangle, triangle PMA. This is the big right triangle PMA that I go with on the original drawing. PA is the hypotenuse PA equals to x units in its length, according to what is given as a question. PM equals to 4 and AM equals to 8. So in this right triangle APM, according to the Pythagoras theorem, PA squared, that is the square of the hypotenuse, must be equal to PM squared plus MA squared. PA is x, therefore PA squared is x squared, and it is equals to PM squared. PM is 4, therefore PM squared is 4 squared, that is 16, plus AM squared. AM is 8, therefore AM squared is 8 squared, that is 64. So in total, x squared equals to 16 plus 64, that is 80. So x squared equals to 80. We substituted 80 by 16 times 5, so x squared equals to 16 times 5. Here we took out of this equation and found out that x equals to the square root of 16 times 5. The square root of 16 is 4, so inside the root we left only with 5. So we found out in both methods that AP is equals to x, it is equals to either 4 times square root of 5 units in itself, or in terms of numbers, AP is equals to x, it is equals to 8.94 units in its length. Repeat again, we found out that in both methods, that the length of side AP it is equal to x, it is equals to either 4 times square root of 5 units in its length, or AP is equals to x. In terms of numbers, it is equals to 8.94 units in its length. Okay, thank you very much.